Welcome back, physical geographers. We just finished up internal processes. Now we're going to move to fluvial processes, chapter 16. So here we go. So we have the impact of fluvial processes on the landscape. Streams, stream systems, flow, overland flow, valleys, interfluves, basins, stream orders, which we kind of see what's frequently called headwaters, sometimes freestone streams, essentially where waterways are born, if you will. We have fluvial erosion and deposition, erosion by overland flow, stream flow, and transportation. Also, we have deposition, erosion, stream channels, channel flow, structural relationships, and consequent subsequent streams, antecedent and superimposed streams, and stream drainage patterns. And to finish our outline, we have shaping and reshaping of valleys, deepening, widening, lengthening, deposition in valleys. We have floodplains and landforms, modifying rivers for flood control. Great example of flood control in the Mississippi River, which I grew up on. Very great example of that. And stream rejuvenation. Then we have theories. We'll finish up with theories of landform development, from Davis's geomorphic cycle to Penk's theory of crustal change, slope development, and equilibrium theory. So one of the exciting things about physical geography is that we can actually see what we're studying and discussing. So here's a perfect example of that. You see a meandering stream, a stream being any channeled flow of water. We see fluvial processes involving running water, having overland flow and stream flow. So overland unchanneled, and then stream flow is channeled. So essentially movement of water along the valley bottom. So it's kind of kept within the banks and has a path, if you will. Among stream systems, we have a valley portion of terrain where drainage basin is clearly established. Interfluve, higher land above valley. Drainage basin or watershed contributes to overland flow, stream flow, and groundwater. So we see that kind of being more of a general collection. Drainage divide, line of separation between runoff, descending direction, runoff one drainage basin or runoff to another drainage basin, and so forth. Really, once again, basin, you can think of collection. So, nested hierarchy of drainage basins, we have several in the United States, for example. Here we have Mississippi River drainage basin, so it's essentially anything that would go flow into that river, ultimately being a collection point. You see it comprised of several different smaller basins, so it's nested, meaning one kind of leads to another, or kind of rolls up, or is comprised of another. So that kind of helps us understand stream order. So we have, earlier I referred to headwaters, and then I was leading to tailwaters. So when you get into streams, like into the mountains, there's essentially headwaters, which is where the streams are born, if you will, and then you have tailwaters, which are post-dam drainage basins. Now, this can be construed more on a natural basis, but the reality of the matter is many of the stream systems that we have, especially in the United States and very often throughout the world, have dam systems to control flooding and flow and transportation and so forth. So that's why we have the first order, second order, and third order streams. So look over our map here, the freestone streams that I referred to. Part of the reason I refer to that is we see that so often in Colorado. So if you have a freestone stream, there's nothing in between the runoff from the mountains or its source to where the waters collect. Tailwaters are post-dam, so it's gone through a dam and been controlled, which we tend to see different places throughout the state. And in the United States, when you have post-dam waters, they tend to be very controlled and stable. You don't see the water flows up and down as much. Okay. Erosion by overland flow. So we see several different types of erosion: splash, sheet flow, rills coalesce into larger channels, or gully erosions. That's kind of more almost catastrophic events. Gullies get larger, incorporate drainage systems into the valley of the stream flow. So essentially we see gullies as kind of more being isolated, very unique events, and then they kind of get incorporated into the way the flow usually occurs consistently on a day-to-day basis from the event that happened that was so extreme. Okay, so erosion by stream flow, so we see channeled surface flow, increasing volume and speed. That can cause erosion, hydraulic power, moving water, roads, bottoms, and sides. Increased by transport of abrasive debris and rock fragments. Some chemical weathering, especially if we have like acidic rain, that kind of stuff. Erosion rates vary by speed and turbulence of flow also. So we talk about stream load. What can the actual stream carry? So material collecting in it, dissolved load, suspended load. Dissolved in the water is actually carried in the water. Suspended is actually held up by the water, and then bed load is essentially smaller transports and being bounced along, known as saltation. And coarser pieces are moved by traction, so they you can kind of think of something bouncing end over end. Stream competence, measuring the particle size the stream can transport, and capacity, measuring the amount of solid material that can be transported in a stream, which can basically, both of those can vary essentially on time of year and how the stream is, essentially how big is it and how much water and capacity is in it and so forth. We have deposition, stream deposits and sediments, essentially using the same concepts we used before in terms of how deposition and erosion can be handled by the stream itself. We have perennial streams, permanent stream flow, and intermittent. They're kind of more seasonal. And then ephemeral, which we kind of see. Good example of that, if you get on central Arizona, you'll see several streets that basically won't have bridges, but they'll just let the water flow based on an event. It's a good example of that. You often see that in very arid areas. Okay. So flood is agents of erosion and deposition, discharge. We see amount of unit per flood. And collecting stream flow data helps predict flood events. So like the work, for instance, the USGS does. As far as stream gauges, great example of that. Amount of urbanization contributes to flooding, so we essentially can see how quickly it occurs to runoff. And then if there's basically urbanization, there tends to be removal of vegetation, which kind of naturally controls what type of moisture can occur in terms of contributing to erosion and deposition. And we also have events, frequency of events that contribute to erosion and deposition. Data over time can provide the frequency. For instance, a 100-year flood, we know how there's a 1% chance that a flood of a certain size can occur any 1 year. And with channel flow, 3 dimensions of stream flow in a channel. Gradient causes gravitational pull to move the water down. Friction on the sides and the bottom. Turbulent flow caused by friction, internal stresses between currents and channels, surface irregularities. So if we understand wind and some of the pull and wind, a lot of the same concepts are true with gravitational pull to water. Also, when we build water and stormwater and sewer systems, we tend to rely on gravity, which is why we have stormwater running off downward, and then we also pump water upwards to basically water towers, water reservoirs that are much higher than housing, and why the pressure's all controlled. So good to know. It happens naturally, and it also happens man-made. 4 categories of stream channel patterns: straight channels, sinus channels, meandering channels, braided channels. See examples of each of those. And then structural relationships, consequent stream, first to develop along initial slope of land, and then subsequent streams along structural weakness. So we see kind of a little bit more direct erosion on the structural subsequent streams. Antecedent streams predates the existing of uplift by land, maintains course by downward erosion. The superimposed stream, established in higher landscape, but is now mostly entirely eroded away. So we can kind of see the different phases and categories of that. Dendritic strange patterns kind of looks like a tree growing trellis. We see that kind of spread out more. Really more of a function of the land and what essentially the stream is being transported through. We also see radial. Often happens around high surfaces such as volcanoes centripetal, converges into a basin. Annular drainage pattern, soft domes or basins. So once again, the underlying landform and composition really affects that. Trellis we discussed. Okay, so then we could get into valley deepening. Colorado is a great place to see samples of this down cutting. Like for instance, if you go to Gunnison or some of the river gorges that we have around, whether it's Clear Creek or along I-70 or out by Canyon City, so forth. There's plenty of examples, or by Gunnison, many examples of where we see this kind of down cutting, if you will. We have graded streams, stream gradient dropping. You can drive along I-70 in Colorado and see, or drive north on 40 to up to Rocky Mountain National Park and see all kinds of these types of grades dropped, and then nick points, irregularities in channel with turbulent flow. So we see all of a sudden these kick points happening, and then we kind of see valley erosion. So we get up to Rocky Mountain National Park, you can see quite a bit of the oxbow lakes are essentially cut off by the down cutting and the stream actually changing its flow and its bank. So essentially the oxbow lake used to be part of the stream and was kind of cut off through erosion and cut banks, if you will. Okay. Valley land thing, headward erosion, cutting into interfluve upper valley. So we kind of see that in terms of outward force when water is flowing and going around a curve, it's the outside curve. Capture or stream piracy, headward erosion caused by one stream to be diverted to the basin of another stream naturally. So all of a sudden we see one stream moving into another one, essentially. Deltas we see at the bottom of the Mississippi. Deposition landform at the mouth of a river, usually the widest part of a river, entering into a larger water body. Largest deltas and deltaless rivers. See really good examples of that. The mouths and the river deltas. We talked about the Mississippi earlier. Floodplains, low lining areas, usually very rich soil deposited off large river basins, natural levees, and Yazoo streams, tributaries. See examples of that. Flood control along the Mississippi River. Floodplains we discussed. Stream rejuvenation and terraces. This can be natural or man-made. See examples of that. Davis's geomorphic cycle. We can see the phases that streams occur in. And then Penk's theory of crustal change and slope development. Slopes assume various shapes as they erode. So over time, the slope changes, essentially, based on when and where it occurs. Equilibrium theory, we essentially have crustal movement resistance of underlying rock, important in determining the terrain. So the actual landform development and fluvial processes are impacted based on what the water flows over, essentially what's its composition and how well it adjusts to the wear. Yeah, so if